Last time we discussed the AM algorithm, but that was a key problem with the discussion because the algorithm assumed that we already knew the posterior probabilities. That's why we like to estimate them. And one way to do this is the Bayes filter. Suppose a system of equations describing our hidden Markov model has the form xk equals some function of xk minus 1 uk wk and yk equals some function of xk and nk, where uk is the interference, wk is the process noise, and nk is the observation noise. Our goal is to give an estimation of the posterior probabilities, which we'll denote by bel xk. Clearly, bel x0 equals the probability of x0 because, by definition, if we set k equals 0, then there is no condition. For the estimation of the posterior probabilities, we derive a recursion. But first, we would like to prove a lemma which says that in general the probability of x with the condition y and z equals the probability of y with the condition x and z times the probability of x with the condition z, all this divided by the probability of y with the condition z. This lemma follows from the fact that both sides equals with this fraction. The left-hand side trivial equals with this fraction, the right-hand side equals with this fraction, because if we use 3 times in a row the definition of the conditional probability, then we get this expression from this fraction. First time we use the definition of the conditional probability here, then in here, then in here. Now, we would like to prove the proposition which gives us the recursion for the ball xk. And the proposition says that there exists a constant eta such that bell xk is some function of bell xk minus 1. By the lemma above and the Markov property, bell xk equals with this product because we use the previous lemma for the value of the bell xk. Then we denote the 1 divided by this probability fraction by eta and pull out it in front. Then we use the Markov property for the yk. Also, we use a continuous version of the Bayes rule for this expression. From we get this integral over xk minus 1. Then we simplify this expression to this product. We can do this by using the definition of the conditional probability, which says that the probability of xk with the condition xk minus 1 equals the probability of xk and xk minus 1 divided by the probability of xk minus 1, and we multiply both sides with the probability of xk minus 1. In the next step, we use the fact that every yj can be expressed as a function of xj and nj, and also use the Markov property. And last time we noticed that this expression is exactly the definition of bel xk minus 1, and this is what we wanted. Let's look at another application for the Bayes filter. This is the market making and estimating true prices. The market maker's task is to set bid and ask prices at every time t. The true price weight is not directly observable, and we observe it as pt. So our model will be something like this, where vt equals vt minus 1 plus eta t, where eta t is the process noise and the observed price equals the real price plus some observation noise. The Bayes filter, in this case the Kalman filter, which we will discuss later, gives an estimation of the true price and its uncertainty, because the Bayes filter gives an estimation for a distribution, and the distribution right now is a Gaussian distribution, and Vt prime will denote the mean of the distribution, and sigma t will denote the deviation of the distribution. The market maker strategy is then to set the bid at time t this expression and set the ask at time t to this expression, where data covers the transaction costs and gamma is the risk premium. Notice that the larger the uncertainty, the wider the bid-ask spread is, because the bid-ask spread is 2 times delta plus 2 times gamma times sigma t.